Welcome to Higher Structures seminar of Reza Gürsey Center for Physics and Mathematics. Today our speaker is Claudia Scheimbauer, and she is going to talk on the universal property of the higher category of spans, which is joint work with Toshi Valde, and we thank her very much for accepting our seminar invitation. Please, yeah.
Well, conversely, thank you very much for having me. As I mentioned just now, this is one of the first talks I'm giving during my maternity leave, so it's a bit exciting to be back in math. That being said, it was not quite clear to me what the background of everybody is, so I will try to start slowly, but please do help me in, asking questions in between, if things are familiar, but also especially if things are not familiar, please ask for clarifications. I will try to not be very technical on purpose, but if people would like details on some technical stuff, I'm more than happy to give that, just ask. I will try to look at the chat as well. I'm not sure I can see it. Yeah, I'm not sure I can see it, but please let me know if there's a question in the chat. Okay, so what I'm talking about today is joint work with Toshi Valde. It's still in progress, so it's not quite finished yet, but we're quite far. Let me put it that way. And the outline of what I'm going to talk today is, well, the title was actually twice as long, and I shortened it. But we'll start with this part of the title. We'll start with spans. Spans. The second part is my motivation for this project, namely, which is finite gauge theory. So, I mean, you may or may not have heard this word, but finite gauge theory is one of the standard examples of TFT, tight Graph-Witten theory. And in fact, this universal property of the higher category spans allows one to construct finite gauge theories, but I will explain why. And then the third part is a sketch or outline of the proof, or the idea. The proof of the universal property. Okay, so that's the plan. There's one more thing. I hope I can do this at the same time. Yes. So let me see if I can find the chat. Yes, here it is. So what I'm writing is automatically backupped to this Dropbox link. So if you forget something or want to kind of scroll back, feel free to just go there and you will find the PDF of my slides there. And it should automatically back up, hopefully. Okay, so let's see, part one. What are spans? So some of you might be more familiar with the word correspondence. So algebraic geometers tend to use correspondence, topologists spans. And so spans or correspondences go between some spaces or varieties or stacks, something geometric. And let me call these generically X and Y. So let me say a singular, a span or correspondence between spaces, varieties, stacks, X, Y is the data, a triple MFG. Do I want M? No, I want sigma here. Where my F is a map from sigma to X, and my G is a map from sigma to Y. Okay. So this is my definition. And one example here, it's not quite a span. It's more of an opposite thing, but hopefully most of you have seen what a cobordism is. Question? Yeah, okay, great. So a cobordism, M, comes together with an in part. That's the in boundary. and together with an out boundary. So, I mean, it's almost a span, right? Except that the maps go the other direction. So the maps go up instead of down. But it's a span in the opposite category, if you wish. Okay, and so this will also lead us to an actual span, and that will be our motivating example for the second part for finite gauge theory. Now take G, a finite group, and then we can perform maps into BG, the classifying space of G. And so if I do that now to each of these pieces here, what I will get here is maps from M to BG, that's G principal bundles on M. And what I can do with bundles is I can restrict them to the in part, which corresponds to just precomposing with this map. Or I can restrict to the out part, which is precomposing with the other inclusion. And so this is actually a span. And that will be one of the motivating examples actually for our project. Okay, maybe I should draw an example of a cobordism. There has to be one in my talk. Okay. So here is our incoming part and here's our outgoing part. All right, so what about these spans? Part of my title says something about a category of spans. So we need some sort of a category. And how do I assemble this into a category? So we assemble spans into a category. So my objects, and I will, for now, I will stick to spaces, but you could just as well do it with varieties or stacks. My objects are spaces. And I will generically always denote them by XY. My morphisms are maybe I should write a morphism from X to Y is a span from X to Y. So something like I wrote above. Okay, and so how do I compose now? Composition. So let's say I have a second one. And notice now that my target of one of them is the source of the other. And so how do I compose these things? I mean, this is something you might have seen already. A special case of this is a relation. And for relations, you can also compose relations. And if you kind of really track the formula that students usually see in the first year, what is happening is that we're actually taking a pullback here. Okay, so you might object at this point. Pullbacks aren't only defined up to something. So especially, I mean, if we had sets here, we could get away with kind of finding an explicit model for this pullback. But especially if we're in spaces or something with a higher categorical structure, then this pullback really is only defined up to homotopy. And what I mean by pullback here is actually also a homotopy pullback if I'm in spaces. Okay, so this here, maybe I'll write this in red as a warning. This is only defined up to homotopy or something like this. So, I mean, it's well defined in the infinity category of spaces, but I don't know if you know this word. So to fix this, what we do is actually, I lied here a little bit. A morphism is not just a span, but it's actually, I mean, either to make this into an actual category. So here I just wrote category. So to make this into an actual category, I would have to write here homotopy classes of spans. Or, and that's the option that we will actually take, is, I will continue in red because that's the fix here, it assembles into an infinity 1 category. Okay. All right, maybe this is a point where I should mention names. The first person to really properly define this as an infinity 1 category, as far as I know, was Clark Barwick. I mean, and yeah. Okay, so with this definition now, it really is an infinity 1 category. So I don't know if people here are familiar with what this is. If not, maybe just take it with a grain of salt, so that, you know, this is something where there's an extra thing fixing problems like this. Okay, maybe that's one way of saying it. So in spaces, we have something like homotopies, and those homotopies give us something like this infinity here. So those of you who really know what that is, yeah, you will probably laugh at that description, but I think it's best to be a little bit informal here. Of course, you can choose your favorite model for infinity 1 categories and actually produce it as that. Right. So why are we interested in these spans? Or okay. So why are we interested in this? Well, we will be interested, actually, this category has a neat universal property. So, I mean, you know, one thing is that maybe you will be interested in this universal property that this category has. And the other thing is that this universal property will actually tell us something about a field theory that comes from this situation here. So those are our two motivations. Any questions so far before I continue? So let me explain now what the universal property is that we'll want to look at. This infinity 1 category has a universal property. And this was proven by Jonathan Harpas a couple of years ago. So the infinity 1 category of spans of, and I'll leave a gap here on purpose, spaces. And my notation for this will be span infinity 1. And I will often abbreviate this just by span 1. Okay. And this infinity 1 category is, and there will be a property that comes in here, but I will explain that a bit later. And it is universal among these, because I would like to write down the property first. Yeah, or maybe I can put it here. So it's what's called semi-additive. So for other D, which are semi-additive, we have the property that if I map out of my category of spans, and notice here I have my 1, then what I can do is, so my objects, remember my objects were just spaces. So there's a particularly nice, easy space called the point. And so I can evaluate at the point, and I will land in D. And now if I just restrict to functors, which are semi-additive, then this becomes an equivalence. So this here means semi-additive functors. I will explain what this property is in a moment, okay? I will just want to have you see this first, and this is not quite correct yet. We'll get there in a moment. This is not quite correct yet, but I would like to show you, I mean, this is quite powerful, because let's say we want to build such a functor, and building functors is hard, usually. But this tells me that I can just pick any point in my target, in D, and by the universal property, we will automatically get a whole functor. And I mean, what this functor does is the point, it says to my chosen element in D, and the rest just follows. So the rest will be essentially direct sums of that element, and then direct sums of identities of that element.
Is this some sort of Yone dilemma kind of thing?
It's much more powerful than that. It's much more powerful than the Yone dilemma. Yeah. It really is a whole equivalence. It's more, I mean, if you have heard of the cobordism hypothesis, it's more of a statement kind of like that. In the cobordism hypothesis, we look at different types of functors. And then, but we have a similar statement, like we can evaluate at a point, and then we can recover the whole topological field theory from a point. Okay, so let me tell you a little bit about additivity or semi-additivity. Maybe let me change to a different color. So semi-additivity. And there's a space here on purpose, here. So there will be something that's added on, and this formulation is due to Hopkins-Lurie. But I mean, semi-additive ordinary category is something hopefully some of you have seen. I mean, additive categories are special examples. Additive categories enriched in abelian groups. In particular, that's something that we will almost have here. But those are the prime examples. So if you've never seen semi-additive before, please keep in mind the category of vector spaces over a field, or modules over some ring, some things like that. All right, so semi-additivity. So, and we will see the generalization to M. So M is a natural number now. And so for M equals 0, it's the usual semi-additive. So it has a 0 object. So it's initial and terminal. And it has a direct sum. So what this means is that if S is a finite set, then what I can do is I can form the coproduct of some objects indexed by S. I can form the product indexed by S, and actually there's a comparison map. That comparison map is induced by, well, if xi and xi agree, I put the identity. And if xi and xj for I is not j, then I put the 0 map. And the 0 map exists because I have a 0 object. And I want this comparison map to be an equivalence. And then that's what I call the direct sum. So if you think of vector spaces, we always talk about the direct sum. But the key nice thing there is that and I should say finite dimensional vector spaces, that the coproduct and the product agree. And that's somehow the crucial thing there. That's something we always use without thinking about it, but really it comes from here. So what is this 0? Is the green visible? Or should I switch to a different color?
Maybe you should switch the paper a bit down. Yeah.
Like this? I'm still here. Is the green visible? Now it's purple. That should be visible. So what's this M? This M is, so for finite sets, that's something sometimes it's called homotopy 0 type, or zero finite space. And that's where we will generalize. So where we actually want to get at is we want to put here M finite spaces, and I will add an M in my notation. And then this will be M semi-additive and M semi-additive here. So that's where we actually want to get at, but I have to tell you what M finite spaces are first. Okay, so M finite space is it has finite pi I for I less than or equal to M, and pi I equals 0 for I greater than M. Okay, so that's an M finite space, or homotopy M type. And those are the things we want to generalize to. So now in this definition here, we have to replace this condition now by something where I can put my S now such an M finite space. Okay, so we assume it's an inductive definition. So we assume that it's M minus 1 semi-additive. And now we replace this condition here. So instead of the co-product, we now take a co-limit. And we take a limit. And there's a comparison map, which I won't explain because that's actually a bit involved. And we require that to be an equivalence. So this is now for S an M finite space. So that's an M semi-additive category. So for every family Xi indexed by S and M finite space, the co-limit and the limit agree. And so I can sometimes denote this by something like a direct sum over S Xi, but here it's clear that, I mean, this is not the usual thing. It's meant to be this thing. So there are some very neat properties. I mean, maybe going back to back to M equals 0, there are some nice properties. And I mean, you can also reformulate the definition in a different way, which makes this into definition. But the nice thing is these are enriched, semi-additive categories are enriched in commutative monoids. So in particular, Hom of X to Y is a commutative monoid. Why I'm kind of elaborating on this will become apparent later. And it has products, or equivalently co-products. And you can generalize this reformulation or these conditions to the M semi-additive setting as well, but I won't really talk about that much. But the neat thing is, yeah, so maybe let's first do an example. So A modules, I told you, keep in mind A modules as an example. So this is always 0 semi-additive. And it is M semi-additive if the characteristic of K, A is a K algebra, the characteristic is 0. So those are that's the running example you should keep in mind. Okay, so the neat thing is really, I mean, it's not at all, at least to me, it was not at all obvious that spans has this condition. So that's actually a very neat thing to try out, to really see that the limit and the co-limit agree there, because in spaces this is certainly not true. In spaces, they're very different. But for spans, this is true. All right, so now we understand the statement here. Are there any questions at this point?
Can I ask something?
Certainly.
These last two properties you wrote, that
yes.
Hom sets being a commutative monoid, how does it generalize if M is bigger than 0?
It's something called an M commutative monoid, which, I mean, the definition is rather involved. I mean, a reformulation is really saying, well, I mean, has a property like this, basically. So it won't really tell you that much a priori. But it's something, I mean, I like to think about it as it's a structure. So in a commutative monoid, what can you do? In a commutative monoid, you know how to multiply things that are indexed by a finite set. And now instead, we have something like this. So now we cannot, like, it's more than a commutative monoid. We can still form a product for things that are indexed by a finite set, but we can form more. We can form a product where things are indexed by some M finite space. So this is much stronger, much more.
I was worried that you wouldn't have maps to each xi from a limit. Is that sort of solved by something else, or?
Yeah, so this, you're asking this, where this map comes from?
No, if you will, to define the monoid structure, I guess you have in the M0 case, use the maps from a product to each
yes.
xi.
Yes.
But here you have a limit, so you don't have maps to each xi, do we?
But it's both a limit and a co-limit. Because this is an equivalence here, it's both. So I have maps. I mean, yes, I have maps in both directions, right?
Okay. Thanks.
Exactly. Good question. Yeah.
Thank you.
So these M commutative monoids are rather mysterious. Like the first time I saw it, I had absolutely no intuition for it, because it's usually we expect it's called something like that. Usually we expect something like maybe a little bit less commutative or more commutative or something. But here it really means that we can actually form such sums over much more general families than we're used to. Actually, this is one of I mean, Harpas's paper explains this in a very nice way. And I mean, this is something that Hopkins and Lurie came to this condition, I mean, sometimes called ambidexterity. And because some like p-local spectra actually have this property. Okay, great. So now the next step is, I mean, this is a theorem. So what's our contribution here? Well, we would like to, or we are proving, or we have a sketch of proof of a higher categorical version of this statement. Okay, so this category of spans, I can actually form a higher category of spans, an n category spans. And then I have a universal property that's really analogous to this one here. So let me explain a little bit what this higher category spans is, and then I will explain to you the TFT motivation, why I care. Okay, I think this is maybe not so important at this moment, let me go back to here so that you see what the spans are. So going higher, so higher means we want an infinity K category of spans between M finite spaces. So this I will denote by span, and then my K will be at the bottom and the M will be at the top as before. So my objects don't change. My objects is the same as before. So M finite spaces. I didn't explicitly write this down before, but this extra decoration of having an M here means that I'm only looking at M finite spaces from now on. And now I have morphisms as before, but this is a higher category, so I will want to have some indexing. So this will be one morphisms. So let me see, these are M finite spaces, then HOM in span Km from S1 to S2. An element in here, well, is just a span, just as before. But now I add two morphisms. And so if I take an object like I did here, but now I also take a second one with the same source and target. Okay. So these are my source and target. This here is my source. This here is my target. And now I want to say what a span is between them. So my new data now is something sitting on top of them. Okay. So this here now my is a span from this span to that span. So that's what a higher category is. In the higher category, I have morphisms between morphisms. This is something that people in the audience usually are familiar with here a little bit. Yes, okay. And now for three morphisms, I want to continue like that. So I will cheat a little bit. Paste this here. But now I have two morphisms. So I will write my guy from before like this. And now I need a second one. This will be my source. And now I need a second one, a target. And my three morphism now will be a new thing at the top. Okay, so hopefully you see how to continue this. And the person who first defined these things rigorously was Rune Hauksing as an infinity K category. So that's what spans are. And all of the things you see here, the SI, the sigmas, these guys, the phi's, they're all M finite spaces. All right. So now I can mention our results and I can cheat a little bit. Zoom talks really have an advantage. So and now I can put in here I don't really have to change that much. The new thing is that now this is a, did I just say K category, right? Yes, KK. If I put a K here, the infinity K category spans of finite spaces is M semi-additive and universal among these. So for D, an infinity K category, we have the same statement here. A priori, at the moment, we have the result for the underlying infinity 1 categories. But actually, I think it should generalize. That's one of the points where we still are in progress and we haven't just worked it out. Okay, so I mean, this is cheating very much because I haven't told you what this means, what M semi-additive infinity K category means. But somehow I really want to show you that really it's very in parallel. And you still have the nice thing that you can construct functors just given a point in here. So let's talk about, before I tell you what M semi-additive means, let me talk about why I care. Because hopefully that will be a motivation why you could care. So I told you finite gauge theory, or Dirac-Witten theory. And the strategy here comes from a beautiful paper by Fried, Hopkins, Lurie, and Telemann. To construct this Dirac-Witten theory as a fully extended TFT, as a TFT really in all senses, via finite sums, or finite path integrals, if you wish. And it goes back to this example that we saw before. So we had the example here of the G principal bundles. So I want to take G bundles, and as such, I mean, what we saw here is that actually if I take G bundles, if I take a cobordism, that was this part, and I take G bundles, then I really get a span. So that means that my G bundles, so I will call this bund G of M. So my G bundles really give me a functor from bordisms to spans, where I send my M to maps from M, BG. So I didn't really tell you much before what I really mean by this. So actually what I mean here is the finite groupoid. So this here is a finite groupoid, i.e. a one finite space. So I'm not sure if everybody's familiar with this. Here we're using homotopy hypothesis and deep things, but not that difficult actually. So just take this as a definition. One finite space is just a finite groupoid. So where we land here is in span 1. And actually we will want to have an oriented version here. It wasn't that important before, but we will want an oriented version. So this is really, I mean, this is what G bundles just do for you. Out of a bordism, they produce for you a span. And I mean, I explained here how to get the one span or just a normal span, but actually this is true in an extended sense as well, for those of you who know what I mean. So this is true for extended bordism category. And so this is my first ingredient somehow in my Dirac-Witten theory. Okay. questions at this point?
Why to one spans? Any intuition about why?
These here?
Yeah.
Really, because I mean, if we want to look at G bundles, we really want to look at them as a finite groupoid. That's somehow classically what you do. You want to look at the G bundles as a finite groupoid, and then the next step, this finite sum, you're counting over these groupoids, basically over this groupoid, basically.
So you one means infinity one category.
This one here means the one semi-additive. That was the decoration here. Okay, and so maybe I can add this.
Okay.
This is one semi-additive. I.e., I want one finite spaces. And that's what I have here.
Thank you.
Maybe I should have given this as an example before of a one finite space, because a groupoid is much more familiar than writing this abstract notion of a one finite space. Okay. So you can take that as a definition. It's actually an infinity K category. So this is where the K is. So here I have my higher version. Here, this is where my K is. So I actually have an infinity K category. Really, this is true for extended Bordisms. From a Bordism between Bordism, you get a span of spans and so on.
Thank you. Thanks.
Okay, so how do we get our Dijkgraaf-Witten theory now? So we can first classical field theory is encoded using what's called spans with coefficients. So let me write my span as before, sigma from S1 to S2. And now this new thing of the coefficients, the coefficients will sit underneath, something like this. So think taking vector space here. Vector space is C equals vect. And this is some symmetric monoidal. In general, it's an infinity K category. You can just think of the one-dimensional case if you wish. That's fine. So what I'm doing here is I'm thinking of these spaces as finite groupoids, right? These are all one finite. So maybe this could be the red from before. One finite spaces, i.e., finite groupoids. So I can map into some category. And actually we have, in addition, we will have a two-morphism here, but I don't want to, it's maybe a little bit too much to explain what that is. But the classical field theory comes encoded as something like this. And so what we have is we have our classical field theory. This is called I usually. Is encoded not just by the map to spans that we had above. This was G bundles. But actually, it should go to span with these coefficients. So here I can forget. That's just forgetting the blue part. And the classical field theory is encoded in such a data. So that means what this means, if you think of taking vector spaces, what this means is that, remember, these were G bundles, right? This is just G bundles. So this part here, that's the part that we had above in the example. So that you should think of as being this here. So what we're doing is, if we're taking vector spaces here, we're picking out a G bundle. For instance, here we're picking out a G bundle and associating to that G bundle something. So, I mean, that's what gauge theory is, right? I mean, you first start with something where it depends on a G bundle. We associate a vector space to our thing where we have picked a G bundle. And now in the second step, we want to integrate out this choice of the G bundle. Okay, so how does this now look? So finite gauge theory. So this is now quantized, is compose I with a finite sum. So we have our I, board K oriented, I going to this funny spans with coefficients. And now we want to integrate out. So this will be called sum K. So in total now, if you think of our example vector spaces, in total we get vector spaces. Okay, and so in total thing, we have a T of T. Okay, good. So that was the motivation. And of course, we want this whole thing in the infinity K setting. I can now show you, I now have a choice. So what I explained to you before was that spans has a universal property. I didn't say anything about spans with the coefficients. That actually also has a universal property. So this uses universal property of spans with the coefficients. So I can either explain this a little bit, or I can start explaining what the infinity K version, what the M semi-additivity means in that setting, and why we expect this to work, or why our proof works, a sketch of proof.
It is up to you. But can I ask one very philosophical question? So this composition in the end you performed gives you a TQFT, right?
Yes.
So my question is, any TQFT can be obtained via this process?
Ooh, any. In general, no. However, if you have particular targets,
right,
then you can prove something along the lines of everything is a gauge theory.
So I mean,
yeah.
So span is more or less like, behaves like some sort of universal category to produce TQFT kind of thing, that I understand.
Yes, that is correct. Yeah.
So it is quite motivic in that respect.
Yes.
Right? Yeah.
I agree. Yeah. So, I mean, this is not true in general, but for, I mean, certainly for particular C's, one can prove that. One can prove that, I mean, in the TQFT, you can look at the object here that governs the TQFT, and you can show that it's equivalent in the sense for TQFTs to one which comes from a gauge theory.
I see.
And so for particular targets, which are natural targets and desired targets, that does work. For the fully general targets, I don't want to claim that. But I do know that Theo Johnson Fried has thoughts along those lines. But you have to be precise about what you mean by C. So one thing I should mention is that this only works here, this second part here, because we use our universal property, you really need that C is M semi-additive, or one semi-additive, right? Because we need the one here. So that's a constraint. You need one semi-additive for this to work. The desired targets for TQFTs that people would like to have should have that property. So vector spaces certainly does, but also higher categorical analogs. There are these higher categories of algebras, bimodules, intertwiners. They should have that property. Fusion categories and so on. They should have that property, etc. So that's the situation I want to restrict to. And in that situation, you can start trying to prove statements like that. That's a great question.
Oh, thank you. So you can continue as you wish, let's say.
Okay, great. So in the couple of minutes that I have left, yeah, maybe I will just explain what the definition is of M semi-additive in the higher context and give you, because we were talking about this 3 examples, just that you have an idea of what these things are. Yeah, maybe that's a better way to continue here. Okay, 3 ingredients for higher version. Okay, so I want to define as M semi-additive infinity K category, C. So let me go back to the definition of M semi-additive that we had before. And in particular, look at these conditions here. Okay. So our ingredients will be, so yeah, this is not a mathematical statement, I should say. An infinity K category C is M semi-additive if, first of all, so from an infinity K category, I can always truncate down to an infinity 1 category. And this should be M semi-additive. So that's the definition that we already have. And the second condition now is that C is enriched in semi-additive infinity K minus 1 categories. So this is really the analog of this situation. Okay. So if I take the underlying 1 category, and now I get the K category by enriching in K minus 1 categories. But I don't want them to be any K minus 1 categories. I want them to be semi-additive, M semi-additive. So you can really view this as the analog of the second statement here as the analog of this situation. So if you wish, an M semi-additive 0 category is an M commutative monoid. Okay. So this is the hierarchy that you're playing. And actually, 1 can be replaced by 1 prime. C has limits or co-limits over S, which is M finite. And so this now is the analog of this situation here. Products were the colimits over zero finite set spaces, so sets. Products are just limits over sets. And so that's the replacement for this condition. So really, I mean, I said properties. This could also have been an equivalent definition, these two. And what we're generalizing here is exactly those two conditions. And so, example, so there's a category called alg, which is an infinity 2 category. So what is this? So my objects are algebras or K-algebras. Morphisms, so I should now say one morphisms, are bimodules. So morphism from A to B is a AB bimodule, and two morphisms are homomorphisms of bimodules. And so this is the analog of the situation that we had before of the vector spaces. So this is always zero semi-additive. And is one semi-additive if the characteristic K equals 0. And I don't want to say anything about higher M because it becomes quite difficult to compute those limits and co-limits. And I just don't know what they are. So it might actually be even more. And so a second example is the 2 category of M semi-additive categories is M semi-additive. And in here we have stable categories, stable infinity categories, if you wish. And we also have to add the adjective semi-additive. But stable infinity categories is something that, I mean, is an important example. And so you add this little property here, which is not too much in that case for stable infinity categories, because they have, limits and co-limits tend to be quite nice. And to also give you a non-example, lincat is not. So this is the category of objects are linear categories. One morphisms are linear functors. And two morphisms are natural transformations. And this is not one semi-additive. I can give you a counterexample if you're interested in this, but right. And so conjecturally, the natural targets that you would like for TQFT, things like fusion categories and so on, they have these semi-additivity properties that you wish. If not, you did something wrong in the construction of the categories. Okay, so just one word, that these properties are necessary is quite easy to see, actually. So this category of spans, I mean, also the way I showed you, it's very iterative. It always looks the same at every level. So that these are necessary conditions is not very difficult to prove. The tricky thing is to actually show that it's sufficient. And what we do there is we actually show a very nice adjunction between M semi-additive infinity K categories and some monoidal M semi-additive K-1 categories. There's a very nice looping adjunction in some sense, very, very similar to, looping the way we know it. And that's somehow the heart behind this property. Okay, thank you very much for your attention.
Well, we thank you very much. So, any questions or comments?
Is it possible to like very quickly say a few words about how the Harpas or your extension is brewed? Like what's the main ingredients? Or
Absolutely. So it's very different. So ours is very different from Harpas, actually, because we use Harpas inductively. So Harpas does an induction procedure. So he takes the category of spans. Harpas. So he takes the category of spans with whatever decoration you would like here. And ultimately, what we want is we want a functor from spans to our desired target. I think it was called D. That's what we want. And now he takes a sequence of subcategories sitting inside here, which starts with a point. And so the points, we already have the image. And then he shows in this filtration here, he extends along each piece of this filtration by basically con extensions. Okay. And so what's in here is what the pieces of the filtration are, is basically if you look at your spans like this, you add connectivity assumptions on it. So, I mean, this one here is M finite. And so what happens along this is you start with like -1 finite, basically. And then you add, slowly you start adding connectivity. So here you ask for this leg to be something connective and the spaces to be something connective. And then you slowly go up the ladder. That's what Harpas does.
Some sort of Postnikov process? Or?
It feels a bit like that, yes. It feels very much like that, yes, I agree. Yeah. And so what we do is very different in nature. Our strategy is, so our ingredients are, one, we want to use induction. Because, I mean, HOM in span K is just span K minus 1 over S1 cross S2, which is the same thing as span K minus 1 of S1, S2. So here I'm using this version with coefficients. I'm translating this space into an infinity category, and I'm using this version with coefficients. And so now, I mean, you can assume that you already have proven a universal property for the span K minus 1 with coefficients and bootstrap that up. That's somehow the idea behind it. So, and then notice that in span, S is a direct sum over all of its points. That's true in span. I mean, okay, in spaces, S is a co-limit over all of its points, but in this case, the co-limit is also a limit. And span K can be obtained from span K minus 1 by, so in the first step, let me denote this just by A. This is monoidal. So we can deloop it. And we get a K category with just one object. Which is just a point. Okay. And now in the next step, I want to add all spaces as objects by taking freely limits and co-limits, by taking freely direct sums. And so the second step is now that we complete semi-additively. So from before the point, we now get all objects. So instead of, usually this delooping is called B, but now I will add a direct sum symbol here. And now we get a junction, a looping, delooping a junction in this setting. That's our strategy. And then it all boils down to the universal property that we have in the previous step, in the induction step.
Thank you. Thanks.
Any more questions or comments? Oh, so let's thank Claudia Scheimbauer once more.
Thank you very much.
Really excellent and very inspiring talk.
Thank you.
And